Hello. In today's video, I wanted to go through one more example of mathematical induction before we move on to recurrences, recurrence relations later this week. So first of all, if you can recall, mathematical induction is what I use if I want to prove that a statement is true for all n bigger than some base starting point. Like I want to prove that something is true for all n greater than 0, or for all n greater than 1, I want to prove to you that this is true. So the way that I do this is I first establish that the statement is true at the starting point, which is our base case. So I prove to you that the statement works for n equals 0, or the statement works for n equals 1. And then once I've established that it works somewhere, or it works at the beginning, then the next step is to demonstrate how to get from knowing it's true at the beginning to knowing it's true at the next point, and then at the next point, and then at the next point. So what we do for our inductive step is we assume that the statement is true at some point, say for some n equals k. Again, there's nothing special about k. It could be smiley face, it could be any variable, but there's some point where this is true, and I want to show you how to get from knowing it's true for k to knowing it's true for k plus 1. And the reason that this makes sense is because I established the base case, I established that this is true for n equals 0, and then this step tells you how to get from 0 to 1. And then I use this step again, tells me how to get from 1 to 2. And then this step again tells me how to go from 2 to 3. So if you were wondering whether or not it's true for n equals 812, like running this hypothesis inductive step repeatedly can establish that this is true for any number that you're curious about. So anyway, this is the basic principle of induction. I understand that induction is complicated for a lot of people in the first class that they see it. Sometimes it's helpful to have different people, different authors explain it in different ways. So I've gone and linked in the description below some additional resources on mathematical induction. So I want to do one more example for you today of induction. And in order to do that, I'm going to need to first show you the Fibonacci sequence. So the Fibonacci sequence is a famous sequence from mathematics. And the thing about this sequence is that every number in the sequence, is the sum of the two numbers before. So we usually say that like the 0th Fibonacci number is 0, the first Fibonacci number is 1, and then like the second Fibonacci number is, you get that by adding these together. And then you go and add 1 and 1 together, and you get 2. Actually, I think I did not want this, so go and erase that a little bit, right? So, So you add 0 and 1 together and get 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is, I believe, 13. 8 and 13 is 21. So the next Fibonacci number you would get would be 13 plus 21, which is going to be 34. Okay? So the Fibonacci sequence, again, the 0th Fibonacci number is 0, the first Fibonacci number is 1, and then you just go and add the previous 2 to get the next one. So the reason that I wanted to introduce the Fibonacci numbers is that I wrote a program that computes the Fibonacci numbers. So, here's a function in Python that computes the nth Fibonacci number. I actually think my indentation's a little off here, but you'll have to forgive me. Basically what I do is I loop through and I keep adding the previous two Fibonacci numbers to get the next one. And then I return whatever my final answer is. So I'm claiming to you that this program works and computes the nth Fibonacci number for every integer n, let's say, greater than or equal to 1. So I want to say that for n greater than or equal to 1, that I want to show you that let's see, that after actually I want text. Why don't I go and erase that? I think I've got a text tool here. So I want to convince you that after n times, or after, say, k times, or I don't know. Yeah, so after, say x times through the loop, that current is the x plus 1 fib number, and last is the x fib number. Okay, so then, yeah, so I want to convince you that after I run through the loop n minus 1 times, I get the nth Fibonacci number, right? So after I run through it, I guess maybe, yeah, after, I guess, n minus 1 times, that the current is the n fib number, and last is the n minus 1 fib number. This is probably a little bit clearer way to do this. I apologize, I'm still figuring out how to be a successful YouTuber here. So anyway, if I could convince you that this was true for all n greater than or equal to 1, then you would know that this function is computing the nth Fibonacci number because what I return is current, and current, I am claiming, should be the nth Fibonacci number, right? So this is my claim, and I'd now like to prove it to you with induction. So the first step is going to be figuring out the base case. So the base case is going to be n equals 1. So what happens when n equals 1? Well, when n equals 1, we don't go through the loop, right? When n equals 1, we don't go through the loop, and we just have 0, 1, where this is the 1 fib, and this is the 0th fib, right? So this is like, yeah, so base case. Yay! So we have a base case when n equals 1, then we don't run through the loop. Current is the first Fibonacci number. Last holds the 0th Fibonacci number. So this works when n equals 1. Boom, boom, boom. See how this happens? Yes. Okay. No. So, redo. Okay. Okay, so now let's say that this works for some number of times through the loop, right? So this is going to, if you go through, let's say, grab my text. So let's assume that it, assume works for n equals k. So then I know that after k minus 1 times through the loop, we have the kth Fibonacci number right? So n equals k, yes, this is boom. So we know after k minus 1 times through the loop, we have here the kth Fibonacci number and the k plus, let's see, this is the, so going into, so after k, we have current is, no, this is not going to work. So this is, let's say, boom, current is the k-fib, and last is the k minus 1 fib, right? So that's this is what we're assuming. We're assuming now that because it works for k minus 1 times through the loop, after k minus 1 times through the loop, then we have current is k Fibonacci number, last is the k minus first Fibonacci number. And what I'm interested in is what happens when I go one more time through the loop, which is the k plus 1 case. What happens with one more time through the loop? So if I go one more time through the loop, then here last is becoming here the kth fib, right? This is, actually, let's do this in order. So this is going to be the last, before last is the k minus 1 fib, right? I'm just writing in our values that we know. Current must be the kth fib. Okay. Boom. No. Let's, current is the kth fib. Excellent. So current, testing out this tool. I think I'm working on getting a better tool for doing this, but so I have then, okay, the kth minus 1 fib is stored in before last. K fib is stored in the last variable. So now we're going to add together these two things, right? And this is where I guess, the only important step is, right? So this is adding together these two things. And if you remember from let's go and give myself just a little bit more space. Right? If you remember, the next Fibonacci number is the sum of the previous two. So if I add together the kth fib and the k minus 1 fib, then I must be putting into current the next Fibonacci number, which is, so current gets so in this statement here, current is getting to be the sum of last plus before last. Last was the k minus 1 fib. Current is the kth fib. And so then we are correctly computing the k plus first Fibonacci number. Also, the last variable is holding the kth Fibonacci, which is the one before. So what I've tried to talk you through here is that if we assume that after k minus 1 times through the loop that we've computed the kth Fibonacci number, we then step through and walk someone through one more time through the loop, and we can then demonstrate to them, look, if we had the right values in our variable after k minus 1 times through the loop, when we go k times through the loop, we still have the right values in our variables. So, any case, I think that's the demonstration that I wanted to do today, talk you through one more induction proof. If you have any questions, there's live chat sessions available with I and the TAs during the normal class times. I'll post an announcement on Canvas to make sure that everyone knows how to join. Additionally, you can ask questions in the Discord channel, not the Discord channel. You can ask questions in the Slack channel. You can also ask questions on the discussion board in Canvas. So send me email, send the TAs email. Hopefully there should be lots of ways for you to get your questions answered. And the next video is going to be moving on to recurrences, and we will have some fun there with recurrences and recursive functions. So thanks a lot. Please remember to like and subscribe down below so that you can find out about all of our wonderful discrete math videos. And I look forward to seeing you in the future. Thanks a lot.